Hi, and welcome to Allen High School's APIB chemistry class. We're in the midst of talking about acids and bases, and we're going to move right into, yes, you guessed it, good old Rice calculations. Now, in this case, what we're going to be focusing on is percent ionization and calculating Ka or Kb from given pH constants. And then we'll move into common ion. But you'll notice that none of these are any harder than what we saw in the points of our titration curve. So let's jump in. This is, you do at 10. We're dealing with, in this case, benzoic acid. But we don't want to miss out on our checklist. Do we have to do a dilution? Did we add volume to volume? Always ask yourself. The answer is no. Always ask yourself, do I have a stoichiometry? Do I have a strong acid, strong base, any acid plus base, or a soluble salt? And the answer is no. So all I have is my rice, R-I-C-E, and I have HC7. It's kind of a long one. If you wanted to give this a symbolic form, you could, as long as you carefully defined it in the context of your answer. Acids lose an H+, so I'm going to get my conjugate base minus plus my H+. Now, honestly, this is the lazy person's way of writing this. Normally, we would write plus H2O, and an H+ would go from the acid to the water. So a chemical synonym, you can think of it, is this hydronium. I don't think I've really mentioned that much, so I thought it was worth bringing into the conversation at some point here. It's called hydronium, and we can think of it as a symbolic synonym for H+, that proton. Now, in this case, I have a 0.1 molar solution, and its pH is 2.59. And I'm going to calculate the percent ionization for this one. You had one worked out for you in your notes, and I just left that there as a model. And then this is yet another one. So we've got 0.100, none of this, none of this. This is minus A, plus A, plus A. Very much like what? The first point on my titration curve. All right, so we've seen this before. You saw very similar ones in the equilibrium. I strongly recommend, if it's not asked, you do it anyway. You write this in symbolic form, C7H5O2 minus over the original benzoic acid. I'll draw a picture of that in just a minute so you can get a sense of chemically what that looks like at the molecular level. Okay. Now, this time it told me that my pH was 2.59. So I've got my framework. If you don't know where to go, start with this as a framework. It gave me my pH. What the pH means is that I know my H+ at equilibrium. If I take 10 to the minus pH, I know what A is, or my H+ is, at equilibrium. So A, and these are both equal, would be 2.57 times 10 to the minus third squared, and then that's over. Now remember, this is minus A. I got a little sloppy there, but the Ka we don't know yet, but we know A, so there's no reason to neglect it. So this is going to be 0.100 minus 2.257. Don't neglect it if you know it. The only reason we would neglect this value here is if it was an unknown, and it simplifies our math. But there's no reason to neglect it here because it doesn't hurt our math at all. And so if we calculate this, which I realized here I had not finished this calculation, we have 2.57 times 10 to the minus 3 squared divided by 0.1 minus that 2.57. I don't know why I put 2.5 there. I looked up at the wrong problem, I think. times 10 to the minus 3. And we should get a Ka value, if I did that correctly, equal to 6.78 times 10 to the minus 5th for our Ka. And I put the wrong thing in here. This shouldn't be 2.25, so I want you to fix that right there because I don't want to start the video over. So that should be 2.57. All right, and that gives us our Ka. To set up our percent ionization, the whole is my starting point of my acid. The minus A is the part that ionized, and that's simply the H+. So that's 2.57 times 10 to the minus 3, and that would be times 100. And if you cranked out that math, you'd get 2.57. Sorry, I did not calculate this. And I get 2.57%, but I would really love it if y'all would check my algebra there real quick because I want to move on. All right, let's do it. Another one. Calculate the K. Oh, it doesn't tell us what kind it is. Well, hopefully you know a couple of things. One, that ammonia is a weak base, plus it needs to be a Kb or weak base problem because the pH is so freaking high. All right, so look for some clues there. No dilution because I didn't add volume to volume. No stoichiometry because I don't have a strong acid, strong base, soluble salt, or any acid plus base. So I'm going to set up my rice, and I get NH3 plus water. You do have to add the water for a base. You can't simplify a base situation. So that's going to be NH4 plus OH minus. And I have a starting amount of 0.100. Not real worried about the water. None of this, none of this. Minus B. I like to use B so that you know that it's 2 steps in and out of the rice, not 1. No reason to neglect B because we're going to find we have B in this case. Now, to get to B, first off, we'd have to go from pH, which was given to us. So if we go from pH to H+, well, actually, I would go from pH to POH and then to OH minus, frankly. That's how I do it. So if my pH is 11.13, then that means my POH is 2.87, which means my OH, my B value, is 10 to the minus 2.87. Right? If we set up our Kb expression, we would have ammonium ion times hydroxide over ammonia. And I know what B is. That was given by giving me the pH. That gave me my values at equilibrium. And so if I plug all those in for Kb and capture those values, you need to make sure you know how to do that to prepare you for problem solving in class. Notice again, I'm not neglecting what I know. We only neglect what we know. And I got very close to 1.8 times 10 to the minus 5th. Now, technically, this question and the last question should be to 2 sig figs. My guess is AP would give you 2 or 3 sig figs for this question. Okay. Now, the next question is a common ion question. Well, a common ion in acid base, remember we saw a common ion was in the initial column of rice, we add an ion that is in common with the equilibrium we're looking at. Well, in this case, a common ion is a buffer calculation. And you notice that we have a buffer zone in our titration. So this really isn't new mathematics, it's just worded differently. So let's take a look. Did we add volume to volume? Do we have to add a dilution? No. They gave us the molarities. The problem gave us the molarities in the final volume already. Do I have a stoichiometry? I have a weak base. You might want to go ahead and write down, as soon as you identify your weak acid and weak base, you might want to go ahead and write that reaction so you're not tempted to make something complicated with your weak base and your soluble salt. Don't add this. This is not a reactant. It's a common ion. Common ions end up in the eye. So if you write your equilibrium first, that might help you avoid that. Okay, back to our stoichiometry here. I do have a stoichiometry because I have a salt, and it's an ammonium salt. And all ammonium and all nitrate salts are soluble without any exception. So NH4NO3 goes 100% to NH4 plus NO3 minus. Nitrate, it's not going to do much in solution. Okay? You'll see it do a few things in solution when we get to redox, but by and large, especially if it comes in a salt, it's not going to be doing much for us right now. Now, because this is a 1-to-1 mole ratio, what that tells us is that this 0.245 molar goes 100%, and it's a 1-to-1 mole ratio, so this is 0.245 molar. Okay. Now, let's plug those in. Stoichiometries go into the initial of rice. So this is 0.245. This was given as 0.245. And some of you may realize at this stage, right away, you might realize that we're dealing with a buffer. And if we're dealing with a buffer, you don't have to fill out rice. You can hop right into Henderson-Hasselbach. Okay? And Henderson-Hasselbach equation here would be the POH would equal, all right, and we're calculating the pH of this, pKb plus the log of 0.245. And not only is this a buffer zone, but it's an easy buffer zone because those are equivalent to one another. So this is the log of 1, and the log of 1 is 0. You should be able to do that level of estimation. The ratio is 1, the log of 1 is 0. So that means POH is equal to pKb. And so your POH is going to equal 4.74. So if that's your POH, your pH would equal 9.26. Okay? So some of you like that shortcut, and you're going to hop right into that. Others of you prefer to use rice. Rice won't fail you if you fill it out carefully. So I'd have 0.245 minus B, 0.245, sorry. I've seen some of you do it. It's so easy to do that. Just grab the plus B, but don't forget that up there. Okay? Now, KB is to the minus fifth. 0.245 is bigger than 10 or 100 times that. So 100 times this would be 1.8 times 10 to the minus third. The number in front is bigger than that, so I can cancel those. So that means that 1.8 times 10 to the minus fifth is equal to, we've seen this K, so for time's sake, I'm not going to write it. I don't recommend you ever being sloppy like that. We've just seen it quite a few times. So B is equal to 1.8 times 10 to the minus fifth. That means POH, if I took minus the log of this number, is 4.74. And pH is simply 14 minus that. And we get the same thing we got with Henderson-Hasselbach. I just think there's a lot less work. And this is simply your KB. This formula here is simply your KB formula rearranged. algebraically. You'll never have to do that. You pick your poison in this case. Pick the method that you want to use. Just remember, all work leading up to your final answer must be shown in order to receive any credit. All right, we're going to keep going on this track of sort of the random ways these questions can be asked. And our next issue is salt hydrolysis. So until then, this is your best chemistry teacher signing off.